Hi everyone, welcome to the 12th SimVascular tutorial in our summer series. And today I'll be introducing GenBC, which is short for General BCs. So up until this point, you've heard about several different boundary conditions offered in SimVascular. And this includes inflow boundary conditions, outlet resistance BCs, outlet RCRs, as well as coronary BCs. And these are all what we call monolithically implemented boundary conditions, meaning that their analytical solutions have been hard-coded into the finite element flow solver. And while these boundary conditions account for a lot of the use cases in cardiovascular simulations, it would be ideal for us to have a more general way of prescribing boundary conditions in the form of arbitrary user-defined lumped parameter networks. And in addition, you might also notice that these boundary conditions only allow for open loop systems, where the inlets and outlets are completely independent of each other. On the other hand, in closed loop systems, which aren't possible with just these, the inlets and outlets are coupled to each other, and I'll talk about that in just a second. So with these motivations in mind, I'll now introduce GenBC, which is short for General Boundary Conditions. GenBC offers users the freedom to prescribe arbitrary LPNs as inlet or outlet BCs. And it also enables closed loop systems. So that's where you have fully coupled inlets and outlets. And here I'm showing you an example of a closed loop system that's actually from Justin's paper, which was made possible by GenBC. And we can trace the system starting at the outlets here, which take us to the 0D components that represent the systemic arteries and veins. And then we move to the right heart, the pulmonary arteries and the veins, the left heart, and finally back to the aortic inlet. There are two types of coupled surfaces in GenBC, Dirichlet and Neumann. And these terms are defined from the 3D domain's perspective. So a Dirichlet coupled surface is where the 3D domain passes the pressure to the 0D domain. And the 0D domain then takes the pressure, computes the flow, and passes it back to the 3D domain. On the other hand, for a Neumann coupled surface, you have the 3D domain passing the flow to the 0D domain. The 0D domain then takes this flow, computes the pressure, and passes the pressure back to the 3D domain. You can find some GenBC documentation online at our SimVascular website. But right now, I'll give you an overview of the tasks that are required on the user's end. So GenBC was implemented as a Fortran program that gets called by the flow solver, and it uses an explicit fourth-order Runge-Kutta scheme to integrate the ODEs. So what's required of the user is to first make a couple modifications in your input file, solver.inp. We then need to derive the governing ODEs for the desired LPN and implement these ODEs in Fortran within GenBC. And finally, we use a Fortran compiler to generate the GenBC executable. So you can find the GenBC source code in the cylinder example online. And once you extract the contents, you'll see a folder that's named sim files that contains the usual simulation files that you may be used to. But there also lies a folder called GenBC files, and it contains 3 Fortran files as well as a make file. So gnbc.f is the main driver code. Modules.f contains a communication module that allows various functions to access the same variables. And finally, user.f is where you'll make most, if not all, of your changes. So in the remaining time, I'll go through the GenBC source code and also implement a toy example of an aorta iliac model with prescribed inflow and outlet RCRs at the iliacs. So this is an open loop system that could be implemented without GenBC, but it should give you a clear picture of how GenBC works and can also be easily extended to your own arbitrary use cases. So at the aortic inlet, we'll prescribe a half sine wave with 1 Hertz frequency. And note that this is an analytical expression for the flow and doesn't require any ODE. And we can also very easily get rid of the negative half of the sine wave when we code this into USER.f later. So this means that the aortic inlet is a Dirichlet coupled surface, since the 3D domain passes the pressure to the 0D domain, which we actually don't need in this case. And the 0D domain passes the flow to the 3D domain. At the outlets, we'll prescribe RCRs, which do require some derivations. You'll notice that for simple resistors, the relationship between pressure and flow is defined with just algebraic expressions. And so we can actually use an offset to account for the proximal resistor here. And the pressure that's proximal to the capacitor can be described with this ODE, where the right-hand side is the flow going through the capacitor. So now you see that once GenBC has solved for P subscript C with RK4, it can simply offset PC by a factor of Q times RP to arrive at the final pressure that we're going to be passing back to the 3D domain. So it should be clear that these outlets are Neumann coupled surfaces here. So let me switch over to okay. So I'll switch over to my simulation folder here. I already have simulation files that were set up to implement this case using the monolithically implemented inflow and RCR BCs. And so bct.dat is already knows that the inlet face is a Dirichlet surface. And rcrt.dat contains the RCR and the distal pressure values for the two iliac outlets. But we can now do this with GenBC. And you'll notice that I've already copied the GenBC files and the make file here. So let's start off by modifying solver.inp. And over here in the other tab, I have the cylinder example project that you can pull from online. And so we can compare our solver.inp to the cylinder one in the tutorial. And you can notice that what we're missing here is actually a couple lines that tell the solver to look for GenBC. Another thing I wanted to point out is that we should actually keep the command time-varying boundary conditions from file set to true so that the flow solver knows to look for bct.dat and therefore also knows that the inlet is a Dirichlet surface. And you might think, well, bct.dat currently contains my previously prescribed inflow. But if we properly define the inlet surface to be a Dirichlet coupled surface in GenBC, then GenBC will actually overwrite bct.dat with the values that are passed in from the 0D domain. So let's go ahead and copy these two lines over to my solver.inp. And the first command here, like I said, instructs the flow solver to look for the GenBC executable inside your simulation directory. And the second command allows you to set some initialization steps where the 0D 3D coupling doesn't yet happen. And so in these initialization steps, GenBC actually won't be solving for your ODEs, but it'll simply hold the 0D values constant at your initial conditions. And for complex systems, prescribing a couple hundred of these initialization steps can be helpful with convergence. So the next thing you'll want to do is change the outlets from RCR surfaces to Neumann surfaces. Change their corresponding list as well. And similarly, we still have to account for the inlet surface. So like I mentioned, the aortic inlet here is a Dirichlet surface. We only have one in this case. The list of Dirichlet surfaces should be the inlet. And in my case, that has a surface ID of 2. We'll get rid of the RCR values from file command. And then lastly, over here, the number of coupled surfaces should be exactly equal to the number of Neumann surfaces plus the number of Dirichlet surfaces. And so we'll change this to 3. So that completes our changes to solver.inp. And I'll now walk you through gnbc.f, which, like I mentioned, is the driver code. So we start off with some variable declarations, and you'll notice that we call a subroutine called initialize, which is actually defined in USER.f, and it's something that we'll have to modify later. And this includes defining the number of Dirichlet and Neumann surfaces, and also defining initial conditions for all of your unknowns. We can move down a little bit and see that there's a lot of error checking. And over here at line 91, you see that for Dirichlet surfaces, we're reading in the pressures from the 3D domain. For Neumann surfaces, similarly, we're reading the flows in from the 3D domain. And in this block right here, we're reading in all of the initial conditions that are actually set by the user. If we move down some more in this block, we'll see that this is actually the 3/8 rule RK4 algorithm that's integrating your ODEs. And you'll notice that the subroutine find F is called 4 times in each RK step. So this is another subroutine in user.f that we'll have to modify later. And it defines the time derivatives of all of your unknowns. So that's where our derived ODEs will come into play. We can continue to move down. And we see in line 176 here, any defined offsets are added to your integrated unknowns. And the result is also scaled by a conversion factor that's also user defined. And then finally, in this last block here, the initial data is updated with your newly integrated values. And then all of your solutions, and as well as your additional user specified variables, are printed out into a text file that's called all data. And this file, all data, will be in your nprox case folder. So with this basic understanding of GenBC, we can now go ahead and modify user.f. You might notice that there are already lots of comments that are in place to help guide you, and you should only really have to modify the commented places. So we can start working within the subroutine initialize. And the first thing you have to do is to define the pressure and the flow conversion units between the 3D and 0D domains. So for example, if the pressure in your 3D flow solver is in dynes per centimeter square, but you want to define all of your ODEs here in millimeters of mercury, then you want to set P conversion to 1333. And this means that for a Dirichlet surface, when the 3D pressure is passed to GenBC, GenBC will first divide it by 1333 before using it in the ODEs. And similarly for a Neumann surface, before the 0D pressure is passed back to the 3D flow solver, GenBC will multiply it by 1333. So here we'll choose to keep our 0D pressures in dynes per centimeter squared. And so I'll keep this at 1. And the same idea holds for QCon, but this is now for flows. So when prescribing Dirichlet BCs to the inlet, we have to remember that the surface normal points in the opposite direction to the flow. And this is exactly why we have to flip the sign on the inflow waveform. And so sometimes users might find it helpful to set QConf to -1 so that they can define their ODEs without worrying about the sign convention. However, you have to remember that as programmed in GenBC, each of these conversion factors affects both Neumann and Dirichlet surfaces. And so if you have a Dirichlet condition at the inlet, but Neumann conditions at the outlets, and you choose to set qconv to -1, then you may want to comment out the relevant lines in GenBC that scale the input flows for Neumann surfaces. So in our case, we can easily flip the sign on our analytical sine waveform. And so let's just keep qconv at +1 here. The next step is to change the number of Dirichlet and Neumann surfaces. So this has to match exactly what's defined in solver.inp. So we do indeed have one Dirichlet surface here, that's the inlet, but we have two Neumann surfaces. Next, for the number of unknowns, we have 3 here. And so that includes the 2 pressures that are proximal to the RCR capacitors at the outlets. And then the third one is the flow to the inlet. So we'll go ahead and change this to 3 here. But note that the number of unknowns does not necessarily equal the number of Dirichlet surfaces plus the number of Neumann surfaces, since you might have more complex LPNs that require additional intermediate variables. Over here, this is defining the number of RK time steps for each 3D time step. And so if you define a higher number of RK time steps, then the code will be much more accurate, but it will also be more costly. We can keep this at 100 for now. So nxprint is the number of additional variables that a user might want to print to all data. So this is in addition to the number of unknowns, which will already by default be printed to all data. So let's change this to 5 right now, and we can define what exactly these variables we're printing are later. The next thing to do in the initialize subroutine is to change our initial conditions. So I'd like to define my initial conditions in the form of an array. So let's just first clarify the order of our unknowns. Let's have the 2 pressures proximal to the RCR capacitors at the outlets come first, and then followed by the flow to the inlet. So let's define this as an array in Fortran. And let's say that the initial pressures I want are at 100 millimeters of mercury. So remember, we're keeping this in CGS units here. So that's dynes per centimeter squared. I have 2 of these pressures. And the last initial condition is for the flow at the inlet. And I'll set this to 0. Okay, so that brings us to the surface to X pointers. And these are pointers that map the Dirichlet and the Neumann surface lists that are defined in solver.inp to your GenBC unknowns. So more specifically, surf to X D pointer must be exactly n Dirichlet surfs long, which is 1 in our case. And since the inflow is our 3rd unknown here, we'll put in 3. This lets the flow solver know that the 3rd unknown should be prescribed to the Dirichlet surface that's defined in solver.inp, which is the inlet surface with ID 2. And similarly, surface.x pointer must be exactly n nNeumannSrfs long, which is 2 in our case. And the RCR unknowns are our first 2 unknowns here, so we'll put in 1 and 2. So this lets the flow solver know that the 1st and 2nd unknowns should be prescribed to the Neumann surfaces that are defined in solver.inp, and those are the outlets with surface IDs 3 and 4. So that finally concludes all of our changes to the initialize subroutine. And we can now move on to defining our ODEs in the find-at subroutine. If we look at the arguments here, we have the time t, we have the array of solutions x, the array of time derivatives f with the same length as x, and we see that f is meant to be passed out, and so we'll be modifying f in this subroutine. And in addition, we have access to the 3D flows for all Neumann surfaces and the 3D pressures for all Dirichlet surfaces. And the ordering of P corresponds exactly to that of surface dot surface to XD pointer, and the ordering of Q corresponds exactly to that of surf to X pointer. So the first thing I want to do right now is to define parameters, and these are essentially all the parameters that we'll need in our ODEs. So here we should define the RCR values, define the distal pressure for the RCRs, and also the value of pi, which we'll need for the sine wave. And we can actually define them as Fortran parameters to prevent them from being changed by the program. So let's do that here. And since we have two sets of RCRs here, let's define this as an array as well, an array of parameters. So let's say this is some example value. And we'll keep it the same for the two outlets right now. We also need capacitances and distal resistances. Let's just say that the distal resistances are 10 times that of the proximal resistances. And the last thing we want to do is define our distal pressure. Again, this is all in CJS. And that's the value of pi. Okay, so when it comes to defining f, which is the time derivatives of all of your unknowns, well, remember that the first two ODEs should govern the first two unknowns. So that's the two pressures that are proximal to the RCR capacitors in our case. And we'll have to divide the ODE that we previously derived through by C just to isolate the time derivative. And also important to note, we can index these arrays with slice notation. So let me go ahead and define the ODEs. So I could say 1 to 2, or I could keep this a little more general and say 1 to the number of Neumann surfaces. So this is exactly what we derived before, but now I'm dividing through by the capacitances. You'll notice that in Fortran, we actually have a max number of characters that are allowed per line. So I do have to move this back a little bit. Okay. So that's exactly what the first two ODEs should be. And remember that we have to offset these pressures by the flow times the proximal resistances. So I'll define these in the offset array. So for the inflow, since we already have the analytical expression and don't actually need to integrate an ODE, we can set the time derivative to 0 and directly set the flow. And we'll also remember to flip the sign and also to remove the second half of the sine waveform. So let's do that here. This would be the third element of f, where we can keep it a little more general and say nNeumannSrfs plus 1. Again, we're setting the time derivative to 0 here, and actually directly prescribing the flow value as its analytical form. So we'll flip the sign here. This is 100 times the sine wave. And we already have the pi that's defined above. Okay, so the next thing to do is to take care of removing the negative half of the sine wave. So we can easily do that with an if statement in Fortran. Remember the negative sign convention. So this is if the flow value is greater than 0, we'll set it to 0. So that's all of our ODEs now. And the last thing to do is to define our additional print variables. So let's print out the 3D flows that are passed to the Neumann surfaces. Let's print out their offsets, and let's also print out the time. Those are the flows. The offset. And the last thing we want to print here is the time. So that concludes all of our modifications to GenBC. And the last thing I want to point out is that depending on the number of unknowns or the number of additional print variables, you might have to increase the length of the string that's defined in gnbc.f over here. So right now it's defined to take 8,048 characters, but you may want to increase this to print out additional variables to all data.